Hello students, happy morning. Class 12 Physics, Unit 7, Wave Optics continuation video. In our previous class, we discussed the phenomena that shows the wave nature of light, that is diffraction. We know diffraction means bending of waves. Okay. We know in order to diffract the light, the opening width of the slit that is comparable to the wavelength of the light. At that instant only diffraction is possible. Okay. We know diffraction. That means bending of waves. Bending of waves. In order to diffract the light, the opening of the slit, okay, the width of the slit that is comparable to the wavelength of the light. Slit width will be greater than lambda, or that will be comparable to the wavelength. Okay, for this case only diffraction is possible. Here our today's topic is diffraction in grating. Diffraction in grating. With the help of the grating, here let me diffract the light. Okay, in order to find the wavelength. Find the wavelength of the light used. Okay, first of all we need to know what is grating. Grating having the multiple slit. Okay, it is nothing but a transparent glass. Transparent glass. Okay, here on which some opaque rulings are drawn. Okay, it is nothing but a transparent glass on which opaque rulings are drawn. Here in modern plane transmission grating, there will be 6,000 lines drawn in 1 centimeter. Okay, 6,000 lines per centimeter. See, this is the plane transmission grating. Okay, here it is a transparent material. Here on which there will be 15,000 lines in 1 inch. Okay, there will be 15,000 lines in 1 inch. This is drawn with the help of the diamond pointer. Okay, not manually, that is by the diamond pointer. Okay, they are representing 15,000 lines in 1 inch. We know very well 1 inch that is equal to 2.54 centimeter. Okay, on solving this we get 15,000 lines by 1 inch became 2.54 centimeter. On solving this we get approximately 6,000 lines drawn in 1 centimeter. Okay, see, this is the diffraction grating, that transparent glass. Okay, this one here on which there will be n number of rulings are there, that here for this is 6,000 lines in 1 centimeter. Okay, this is that line. That lines behave as a opaque medium. Okay, see, this transparent part is known as slit. This opaque part is known as ruling. The width of the slit is A and the width of the ruling is B. Okay, here the combined width of slit and the ruling, that is known as grating element E. This is known as one grating element. This is known as one grating element. This is known as one grating element. We can say this one also one grating element. Okay, this one also one grating element. Okay, that must be equal to A plus B. That is known as grating element. Here I consider a grating element that is named as AB. Okay, here this is a grating element. This grating element having the n number of slits and ruling. Here this is opening is known as slit. This one is obstacle is known as ruling. Okay, here I am using a monochromatic light. Okay, having the wavelength lambda that is comparable to the width of the slit. Okay, here I am using a plain wavefront. These are the plain wavefront from the slit. Okay, on its path I am placing a biconvex lens, that is a converging lens. Okay, then at the focal length of the lens I am placing the screen. Okay, then we know all the rays that are parallel to one another, they are at in phase and they meet at the point O. Okay, for that there will be no path difference. For these waves. They meet at the point P. Okay, at point P there will be no path difference. That means path difference is same. Okay, then next we know according to Huygens principle, all the point on the wavefront that behave as a source for secondary wavelet. Okay, so far I consider one more wavefronts according to Huygens principle drawn like this. That are parallel to one another. So at the point P on the screen it meet at the point. Okay, at the point P that are intersecting. Okay, the point P will be suppose bright. Okay, here it is an angle between the diffracted wave and the direct wave, theta. Here the point P will be bright according to the it based on the path difference between the two waves of the adjacent points in a corresponding point. Okay, here I drawn a perpendicular line. Okay, we know this is the path difference delta. Okay, here I draw in a separate manner. This is A and B slit width, then this is a path difference delta. Okay, here this is theta, means this also theta. Okay, so we can write this one is theta. Then we can write path difference, that is path difference between the two waves, that is delta. I am using sin theta. We know sin theta is equal to opposite side by hypotenuse, that is A plus B. So we can write path difference delta is equal to A plus B sin theta. This is equation 1. If the point P is bright, okay, so we know the path difference delta is equal to m lambda. Okay, this is equation 2, equating 1 and 2. Then we get A plus B sin theta is equal to m lambda. Okay, here we know A is a width of the slit, and B is the width of the ruling, and theta is the angle of diffraction. And m is the order of diffraction. Okay, here lambda is the wavelength of the monochromatic light. Here we are used the monochromatic light. Okay, wavelength of light. Here A plus B sin theta is equal to m lambda is a condition for the point P to be various maxima. If suppose the point P is 0th maxima, so we can write m is equal to 0, then A plus B sin theta that is equal to 0, then the theta value will be 0. Okay, this shows the central maxima that is in a angle of 0 degree. Okay, then the point P to be first maxima. P is first maxima. For that we can put m is equal to 1, then we get a plus b sin theta 1 is equal to lambda. Okay, here theta 1 is the angle for getting the first maxima. Okay, then for point P is second maxima, m is equal to 2, we can write a plus b sin theta 2 is equal to 2 lambda. Okay, then condition for mth maxima. Condition for mth maxima, that is we know a plus b sin theta that is equal to m lambda. Okay, on both the side of the central maxima there will be a higher order maxima. Okay, see, this is the central maxima. On both the side of the central maxima there will be a higher order maxima. That means this is a first maxima, this is also a first maxima, this is a central maxima. Okay, on both the side of the central maxima there will be higher order maxima. Okay, we can write this equation as in terms of n. We need to know first of all what is grating element. We know grating element is a combined width of the slit and the width of the slit and the ruling. Okay, here there are n number of grating elements are there. Okay, in 1 meter length, that can be written as a plus b n, that is equal to 1 meter. In 1 meter length of the grating there will be a plus b n grating elements are there. So we can write n is equal to 1 by a plus b. Here n is the number of grating elements in 1 unit length. Okay, number of grating element in 1 unit length, that means 1 meter length. Okay, we can write the equation as we know n is equal to 1 by a plus b. We know a plus b sin theta is equal to m lambda. So we can write this one in terms of 1 by n sin theta is equal to m lambda. Okay, then sin theta is equal to n m lambda. Here we know theta is angle of diffraction, n is the number of grating element in 1 unit length, and m is the order of diffraction, and lambda is a wavelength that we used. Okay, with the help of the equation let me see how to find the wavelength of monochromatic source as well as polychromatic source. Okay, our next topic, that is an experiment to determine the wavelength of the monochromatic light. Okay, determination of wavelength okay, using grating and spectrometer. Okay, we know by using this relation we can find easily the wavelength. Okay, we need wavelength lambda is equal to sin theta by n into m. Okay, this n is already given in the grating element. We need to know theta value and m. Okay, order of diffraction and angle of diffraction. That's why we are using the spectrometer. Okay, see how to find the angle, that means wavelength of the light with the help of the diffracted angle and the order of diffraction with the help of spectrometer. Okay, in spectrometer the important 3 things are collimator, telescope, then rotating table. Here this is our practical experiment. 2 practical experiments are there. First one is to find the wavelength of monochromatic light. Okay, wavelength of monochromatic light. Monochromatic light, that means single color light The source of this monochromatic light is sodium vapor lamp. Okay, this produce yellow color light. And wavelength of polychromatic light. The source of polychromatic light is mercury vapor lamp. That produce white light. We know in white light there will be a composite color. Okay, that will be VGR. By using the formula lambda is equal to sin theta by nm, we can find the wavelength of monochromatic light as well as the polychromatic light. That means violet, indigo, blue, green, yellow, orange, red. Okay, wavelength of monochromatic light. Okay, we know the formula lambda is equal to sin theta by n into m. Okay, we need to find theta and m. That means angle of diffraction and order of diffraction. We know the value of n. Okay, first of all, I use a monochromatic source, that is from a sodium vapor lamp. Okay, the light from the source that is allowed to fall on a collimator. Here collimator having the slit, that slit find the ray. At the direct point there will be a telescope. The telescope may enter the direct ray. Okay, between the collimator and telescope there will be a diffraction grating. Okay, we know the diffraction grating, the diffract the waves. Okay, this is the direct ray that is obtained at point O. Okay, we already discussed this one without path difference. Okay, then I am rotating the telescope towards the right. Then I get the first order diffracted ray, m is equal to 1. Then I get the image here. Okay, the angle between the undiffracted ray and the diffracted ray is known as angle of diffraction, that is theta 1. If suppose I move the telescope again towards right, right, then I get the same image, that is a second order image, that also said to be theta 1. Okay, then I am rotating the telescope towards left at the same angle theta 1, I get the diffracted image. Okay, first order diffraction, this is 1. Okay, we know the angle and order, then we can easily find the wavelength of this monochromatic source from sodium vapor lamp. Okay, then next wavelength of polychromatic source. Polychromatic source with the help of the spectrometer. Okay, that is polychromatic source, that means white light is spread by mercury vapor lamp. Okay, at its path there will be a collimator of the spectrometer. It have the slit finds the ray. Okay, here there will be a telescope. We can observe the ray that will be white. Okay, at that path there will be a grating. Okay, we know the grating diffract the wave. Then I move the telescope here. Okay, this point, then I get the pattern of VGR. Okay, that start from violet to red. This is a first order image, m is equal to 1. Again, then rotating the telescope towards the right, then I get a second order image. We get VGR, violet to red. Then I move the telescope through towards right side. Okay, at that instant also I get a same pattern VGR, that is m is equal to 1. And second order image, after that we get a second order image, violet to red. Okay, from this is known as angle of diffraction for particular colors. Okay, from this we understood that if angle of diffraction increases, wavelength also increases. Okay, we know lambda is equal to sin theta by n m. If suppose in order to find the wavelength of the red, then we can put the diffractal angle of red. Okay, in which order? That's one. Okay, then next topic is resolution. Resolution. If the image is said to be clear, then the image is at a high resolution. Okay, resolution means to get clear image. To get clear image, it says the clarity of the image. If resolution more, then the clarity of the image also more. Okay, we know the image formation is only due to diffraction. If having a single slit, there will be 2 point sources are there. Okay, here there will be a screen. This object image is there, and this object image will be appear here. Okay, then here there is no path difference, so there will be maxima. Okay, here also there is no path difference, so it will be maxima. This is a diffraction pattern. Okay, we know in diffraction the condition for first minima. Okay, in diffraction condition for first minima, that is condition for first minima. Okay, here it is said to be a rectangular slit. Okay, rectangular slit. For the rectangular slit, the condition for first minima, that is a sin theta is equal to m lambda. We know first minima m is equal to 1, so we can write a sin theta is equal to lambda. Okay, here it is only for the rectangular slit. Okay, here most of the optical instrument uses the not using the rectangular slit, they are using the circular slit. Circular slit, that is in the shape of convex lens. Okay, for that the condition for first minima will be a sin theta is equal to 1.22 lambda. Okay, in rectangular slit we get a diffraction pattern like this: central maxima, then followed by that minima. Okay, this is the diffraction pattern obtained in rectangular slit. Okay, here in a circular slit. Okay, this is that circular slit, this is the screen, this is the focus of that slit. Okay, here the rays are in this way. Here this is a central maxima. Okay, and followed by that first order minima. Okay, this is angle theta, this value is f, this is the r naught, radius of the central maxima. The pattern will be like this: r naught. Okay, this is the radius of the central maxima. By geometry we know theta is equal to r naught by f. Okay, here the theta value will be small, so we can consider sin theta is equal to theta. We can say theta is equal to 1.22 lambda by e. Here this is equation 1, this is equation 2. Okay, on equating these two, then we get r naught is equal to 1.22 lambda by a into f. Okay, this is known as spatial resolution. Then theta is equal to 1.22 lambda by a, that is known as angular resolution. Okay, if suppose I consider here two images. Okay, two images that producing a diffraction pattern. Here it is a first image, here it is a second image of the diffraction pattern. This is a central maxima. These two are central maxima of the both the images. These two images, this one is a bright, this one also bright, here it is dark. Okay, we can say these two are these two are separated images, so it is a resolved image. resolved image. Okay, we can differentiate the two image because there will be a dark band. Okay, if suppose next case, here it is a central maxima of one image, here it is a one more image. Okay, these two images are overlapped. Okay, here there is a no dark, this is a unresolved image, Okay, then next case, that is the first image, then it will be a second image. Okay, see, this is the radius r0, this is also a radius r0, radius of the central maxima. Okay, for this case it is a just resolved condition, we can say this is approximately two image. Okay, this one we can say this is actually two image, we can say this is a single image. Okay, that depends only on the distance between the two central maxima. Okay, if d is greater than r0, then the image will be resolved image. Okay, if d is less than r0, that is a unresolved image. If d is equal to r0, okay, d is equal to r0, that is a just resolved image. This is known as Rayleigh Criterion. This will says, for just resolved images, the central maxima of one image that coincide with the minima, okay, first minima of other image. This is known as Rayleigh Criterion. Okay, for better resolution, the wavelength of the light is small and the size of the aperture, okay, that A value will be large for better resolution. Then let me see what is resolving power. Okay, resolving power, that is important for the optical instrument. Resolving power is the ability of an optical instrument to distinguish the two objects, okay, that can separate the two objects, maximas of the two objects. Okay, that is known as resolving power. Resolving power is the ability of the optical instrument. Okay, the resolution and the resolving powers are inversely proportional. Okay, that means reciprocal to one another. Thank you.